Hey everyone, and welcome back for another deep dive. This time we're really venturing into some uncharted territory.
Oh, I like
We're
that.
taking a deep dive into Roberto Emparan's Illuminating the Dark Side of the Universe.
Yeah,
So you've been exploring the book, and we're here to help you unearth some of the most mind-blowing insights.
definitely.
Buckle up, because we're about to unravel the mysteries of Einstein, gravity, and the symphony of the cosmos.
And I have a feeling this is one symphony we'll be feeling as much as hearing by the time we're done.
That's what I love about Emperon's writing. He takes these really complex, these really big concepts
Right.
and makes them not just understandable, but almost tangible.
I agree.
Like we've all heard that story about Einstein failing math in school, right?
Right, complete myth
Yeah.
that Emparan debunks right away. Turns out Einstein excelled in math, especially geometry.
Interesting.
Yeah, it was actually physics where he clashed with some of his professors' more rigid teaching styles, which, when you think about it, makes his later breakthroughs even more impressive, right?
Oh, absolutely. Makes you wonder how many other, like, famous failures
Right.
were actually just unconventional thinkers pushing boundaries.
Yes.
Speaking of pushing boundaries, let's dive into how Einstein revolutionized our understanding of gravity.
Okay.
And Perron talks about Einstein's happiest thought, the moment he realized a person in free fall doesn't feel their own weight.
And that simple thought, that simple realization, sparked a decade-long quest to understand gravity in a whole new way.
Wow.
Yeah. I had a physics professor who used to say, the best physicists never lose that childlike sense of wonder.
I love that.
Einstein's free fall epiphany, it perfectly embodies that.
It's like that feeling you get on a roller coaster, that split second when you're plunging down and your stomach leaks into your throat.
Yeah.
It's terrifying and exhilarating all at once. But for Einstein, that feeling, a very specific feeling, it held the key to unlocking a deeper understanding of the universe.
Exactly. That feeling led him to the principle of equivalence, the idea that gravity and acceleration are essentially two sides of the same coin.
Okay.
Imagine being in a spaceship, no windows, can't see outside.
Okay.
Is it accelerating upward, or are you being pulled down by gravity? Einstein showed there's no way to tell the difference.
Okay, my mind is already starting to bend a little here, but I'm with you.
Okay, good.
So how does this equivalence, this link between gravity and acceleration, lead to this whole idea of space-time?
Emparan uses this fantastic analogy. Imagine space-time as a giant trampoline.
Okay.
A bowling ball placed on that trampoline, it creates a dip, a curvature, right?
Right.
Massive objects, like stars and planets, do the same thing to space-time.
Wow.
They warp the fabric of the universe around them.
Hold on. So you're saying gravity isn't actually a force, like some invisible string pulling things together?
It's not a force, no.
It's more like objects are just following the curves on a cosmic trampoline.
It's a pretty mind-blowing concept, right?
Yeah.
Instead of a force pulling you down, it's space-time curving beneath you, guiding your path.
Whoa.
It's like instead of the bowling ball reaching out to grab the marble rolling nearby, the trampoline itself is guiding their interaction. That's Einstein, the gravity.
So what does this warped space-time, this cosmic trampoline, have to do with gravitational waves? Emperon keeps hinting at a connection, and I have to admit, I'm hooked. Right? So we've got this image of space-time as this giant flexible sheet, warped by massive objects.
Yeah.
It's a wild concept to wrap your head around.
It is.
But Eperon doesn't stop there. He takes it a step further
He does.
and introduces this idea of gravitational waves.
And here's where the analogy gets really interesting.
Okay.
If you can imagine disturbing that trampoline, say by dropping another bowling ball on it, what happens?
Or send ripples out across the entire sheet, right?
Exactly. Those ripples are like gravitational waves
Wow.
propagating disturbances in the fabric of space-time itself.
Okay.
Just like sound waves travel through air, gravitational waves travel through this fabric of the universe.
And Perron really emphasizes that comparison to sound.
Right.
And it's such a powerful image. It's like the universe isn't just this silent movie playing out before us.
Right.
It's got a soundtrack too, but one we're just beginning to hear.
And what a soundtrack it is. These waves are generated by some of the most violent events in the cosmos. Collisions of black holes, explosions of stars, even the echo of the Big Bang itself.
It's mind-boggling.
Yeah.
And to think, we haven't always had the ability to listen to this cosmic symphony.
We haven't.
And Perron tells the story of Joseph Weber, this pioneer who dedicated his life to detecting these elusive waves.
Weber was a true visionary, way ahead of his time back in the 1960s.
Yeah.
He built these enormous aluminum cylinders, almost like giant tuning forks,
Oh,
hoping they'd vibrate when a gravitational wave passed through.
really?
He even claimed to have detected them.
Huh. Though that turned out to be. Well, let's just say science takes a lot of verification.
Right.
It does.
But that's what's so inspiring about Weber's story.
Yeah.
He had this unshakable belief, this conviction that gravitational waves were real, even when many doubted him. And it
Mhm.
took decades and a whole new level of technology to finally prove him right.
And that's where LIGO comes in. Imagine, if you will, two 4-kilometer-long tunnels arranged in an L shape with a powerful laser beam bouncing between mirrors inside each arm.
Okay, I'm picturing it. It sounds incredibly precise.
That's because it has to be. LIGO is designed to detect the tiniest stretching and squeezing of space-time caused by a passing gravitational wave.
Wow.
We're talking about measuring changes in distance smaller than the width of a proton. To put it in perspective, it's like measuring the Earth's diameter changing by the width of a human hair.
It sounds almost impossible, but it works.
It does. In 2015, LIGO made history by detecting its first gravitational wave signal.
Wow, okay.
The signal, a brief chirp lasting a fraction of a second,
Okay.
came from two black holes colliding billions of light years away.
Wait, so you're telling me this signal traveled for billions of years before LIGO caught it? That's mind-blowing.
It is incredible, isn't it? And think about what it means. That signal, that faint whisper from across the universe, it carried information about these massive objects, their sizes, their spins, the very moment they merged into one.
It's like listening to a cosmic drumbeat, a message from the other side of the universe. And this message, it told us something about black holes, those enigmatic objects that warp space-time more than anything else, right?
Yeah. Black holes are like the rock stars of the cosmos, and Emparan does a fantastic job of explaining why they're so fascinating.
Yeah.
Imagine a region of space-time so dense, so gravitationally extreme that nothing, not even light, can escape its pull.
Okay, I'm officially intimidated by black holes,
Yeah.
but also I kind of want to learn everything about them.
Right.
Yeah.
And we're just scratching the surface. LIGO's detection of colliding black holes, it wasn't just a confirmation of Einstein's theories, it was the birth of a whole new field, gravitational wave astronomy.
It's like we've had this whole symphony playing around us, and we've only just opened our ears.
Yeah, it's incredible, isn't it?
What's so cool about Emparan's book is he doesn't just explain the science. He makes you feel like you're part of this cosmic quest for knowledge.
He's got that rare gift, to make you feel both humbled by the vastness of the universe, but then also incredibly excited about what we might discover next.
Exactly. So where do we go from here? We've talked about Einstein's genius, LIGO's incredible technology, the awe-inspiring power of black holes.
Right.
But what about the future? Emparan hints at even more amazing things to come.
And he's right to be excited. Remember, gravitational wave astronomy is still in its infancy.
Right.
It's like we've just built our first incredibly sensitive telescope, but instead of looking at light, we're listening for these ripples in space-time. Think what wonders are still hidden from our view.
I love that analogy. It really puts it in perspective. So if LIGO is our first ear on the cosmos, what's next?
Well, for one, there's LISA, the Laser Interferometer Space Antenna. Imagine LIGO's precision, but on a colossal scale, with 3 spacecraft orbiting the sun millions of kilometers apart.
Millions of kilometers.
Okay.
That's just showing off at this point.
Yeah.
But seriously, why do we need gravitational wave detectors in space?
That's a great question. Here on Earth, you see, we're constantly bombarded by vibrations from traffic. Even the wind can interfere with LIGO's really delicate measurements.
Right.
Space offers this pristine silence, allowing us to hear even fainter whispers from the universe.
So Lisa will be like tuning out the noise of the city to finally hear the birds sing. I like that. What kind of cosmic songs will Lisa help us hear that LIGO can't?
Oh, Lisa's going to open up a whole new realm of possibilities.
Yeah.
It'll be sensitive enough to detect the mergers of supermassive black holes, the
Okay.
behemoths that lurk at the heart of galaxies.
We're talking black holes, millions, even billions of times the mass of our sun, right?
Right.
That's a symphony on a whole other level.
Exactly. And by studying these events, we can learn about how galaxies evolve, how these giants influence the cosmic web of stars and planets, maybe even find clues about dark matter, that mysterious substance that makes up most of the universe's mass.
Dark matter, There's another one of those mind-bending mysteries. So what you're saying is gravitational waves aren't just about these spectacular collisions and explosions.
Right.
They're also a tool, a way for us to probe the deepest secrets of the universe.
Precisely. It's like we've been studying a silent film for centuries, and now we have sound. And with each new observation, with each faint chirp or rumble LIGO and Lisa detect, the story of the universe becomes a little clearer.
You know, when you put it that way, it's almost poetic.
It is.
And Paran ends his book by asking, if we can now hear the universe, what other senses might we develop? That's a question that's going to stick with me for a while.
And that's the mark of a truly great book, isn't it? It doesn't just give you answers, it leaves you with that sense of wonder, that thirst for exploration.
I couldn't agree more. Roberto Emparan's Illuminating the Dark Side of the Universe is a must-read for anyone who's ever looked up at the night sky and felt a sense of awe and curiosity. If you want to journey to the edges of reality and beyond, to hear the symphony of the cosmos, this book is your guide.
And who knows what new mysteries and wonders await us out there? The universe is full of surprises, and with every new discovery, the symphony only gets grander.
That's all the time we have for today's deep dive, but keep exploring, keep asking questions, and remember, the universe is always listening.